next challenge is entitled Clear Brackets. Create a function brackets that takes a string and checks that the brackets in the math expression are correct. The function should return true or false. So let's look at the examples. We see that the first one returns true because we basically have two sets of parentheses in here. There's this inner statement, subtraction here, and then you've got a pair of parentheses kind of encompassing this whole larger expression as well. There are no mixed and matched parentheses in terms of a closing parenthesis coming before an open one. Any kind of nonsense like that's going to sort of invalidate the statement. And we can see an example of that in number 2, right? Look at this. Right off the bat, we got a closing parenthesis that doesn't make sense if you think about it. It's not grouping anything at all. And then in our final example, notice we have a sign with parentheses here taking its angle, but look at the end, then we got one closing parenthesis, an additional one that never matched up with an opening parenthesis. So if you think about it, you know, the count's got to match. You could imagine even in a statement like this, or like the third example where you have everything matches up, every open parenthesis matches with a closing one, and then you have some extra ones left over, be it opened or closed. That's obviously a problem. So, and that's wrong. So that's kind of what we're going for. That is what we're going for. The notes say the string may not contain brackets, then return true. So if it was just a statement with no brackets, they're calling them brackets. I don't know if that's a regional thing, but we call them parentheses here. So string may contain spaces, and the string may be empty. So those are some nice edge cases to think about. We'll go over to code and implement this. Please pause the video as usual. Make sure you're giving it an honest effort to get the most out of these videos. You're only cheating yourself if you don't. Okay, so I'm going to use a data structure called a stack for this. It's very well suited for this kind of a problem. And I don't think we've talked about stacks. They are what's called a last in, first out data structure. So if you contrast it with a queue, which even if you're not a computer scientist, you know the English usage of a word queue, where maybe you have a music playlist where you queue up songs, right? And you start piling them into a playlist, and they play, the first one you put in plays first, the second one plays second, the third one plays third, etc. And you know, you can have 10 loaded and maybe it's not playing the 10th song yet, but it will play them in the order that you queued them up. A stack, think of it as an inversion of that idea. Your last input item is the first one out when you go to pull something out of this collection. It's designed that way such that you're going to be taking the last element that you put in. And a nice real life example of this is if you think of a stack of dishes that might be in your cupboard. Imagine you're drying them off after washing, and you put one down, then you stack another plate on top of it, and let's say you do this 5 times, so you have 5 plates. When you go to eat dinner, you're gonna pull that top plate off. You know, most of us don't dig under to grab the bottom plate or the third plate. You're gonna grab that one right on top, and you know, if you're serving 3 people, you're gonna take those first 3 right off the top. So that's kind of the idea with the stack, and then we'll see how it's useful in this problem as we go. There is good documentation on the Microsoft docs about this. You can look up the stack. There's one without a generic. I'm using the generic one here, stack T. We're going to be using it with a char. You see the LIFO, that's the acronym for last in, first out. And there is some good reading about stacks in general. There's pretty much 2 really common operations. When you add something to the stack, it's called pushing, and when you remove an element, it's called popping. And then they kind of have a little convenience method called peek, where you can see what the last element is, what's going to be removed next, but you don't actually remove it from the collection, just to take a peek at it. But push and pop are the primary operations on stacks. So let's do that. Let's make a stack, because our string is a bunch of chars, right? So I'm going to make mine of type char, and I'll call mine parentheses new stack, and I'm creating a new object. This is object-oriented programming now. I created an actual stack object with this type of char. Then essentially I'm going to iterate over all of the characters in the string, do some processing there. Yeah, let's move into that. So I'm going to use a simple for each loop, nothing new here, char in string, right? And now if I grab an open if I encounter an open parenthesis, I'm going to push it on my stack, right? And I'll just keep pushing them. We can encounter as many opening parentheses as we want, and that's no problem. You just keep stacking them up. And the idea will be, as soon as we get a matching closing parenthesis, we'll remove one of those ones, one of the opening ones that we saved on the stack. We'll pop it off, and those will poof, disappear. That's considered a match, and then you can see how the count will be decremented by 1 once that pop operation happens, with the idea being that in an ideal case, we're going to match all of the opening ones with closing ones. By the time we're done, the stack is empty. And that's what we're going to do at the end. After we've looped through the entire input, you can say return parentheses, and the stack has a count property that's much like a string length. It just tells you how many elements are in it. That should be in here. Here's count. You can check that method, but it's simple. It does what it sounds like. If that count, return that count is equal to 0. So by the end, everything should be matched up, all the opening and closings. When we got those closing ones, it was pulling an opening one off the stack. And that's sort of how that works. You're pairing them all up, and there should be nothing at the end. Hopefully that's clear. So on to the loop. What do we do in the loop? We're going to check. Our stack's going to hold opening parentheses. So let's check. If ch equals, remember to use single quotes for chars, and I'm going to give it an opening parenthesis. If it does equal that, I'm going to tell it, my stack, to push that opening parenthesis on the stack. So I'm going to push that. Oops. Or yeah, I'm good on parentheses. Okay, so we added one for each. At any time we encounter an open, just push it onto the stack, because it needs to be matched with a closing one to be valid. Okay, in our other case that we're concerned about, remember, we're not going to concern ourselves with operator, mathematical operators, sign text, number values. We don't really care. In terms of this function, all it's worried about are the parentheses, or the brackets as they call them. So those are really the only two characters that we're worried about. So your other case that we care about, if char equals a closing parenthesis, right? That's the other one we want. Well, at this point, right, if we encounter, imagine this, we're just starting in our processing. If you encounter a closing parenthesis with nothing in the stack already, I mean, that's game over right there, right? You've sort of crapped out right there. So let's check the count and make sure it's not 0. If it is 0 and we had a closer, that's bad news. So game over, or we're saying, hey, nope, this is an invalid statement in terms of brackets or parentheses. And then otherwise, assuming there are opening parentheses available to match with, we're just going to simply pop 1 to pair up with this closer right here. So we can say parentheses pop. That should take care of that. And really, I mean, the problem is this simple because we only care about these grouping symbols. So I probably need a using statement for this stack. Let's see what namespace they have. Systems collections generic. Let's add that. Using system collections generic. Okay. Let's give this a run. Looks pretty good from a first scan. Cool, nailed it. Yeah, so I didn't expect you to necessarily know about the stack data structure because I don't think we've talked about it, but it's very common, it's very powerful. It's one you definitely want to get to know. And yeah, hopefully this was clear. The idea is that we're adding opening parentheses as we encounter them. Whenever we get a closer, we sort of remove one that kills off, that forms a pair, and then we never make sure that, or I'm sorry, we always make sure that we don't have an abundance of closing parentheses because that doesn't make sense. If that ever happens, then yeah, game over. And then assuming you went through all of the processing, every opener was matched with a closer, that would have caused every open one that we pushed on to get popped off, right? The same amount that got pushed on got popped off. That's good, and we can say, yeah, make sure that the count's equal to 0 after the processing. And notice we initialize this, so if you get an empty string, right, the count's going to be 0 by default, so that kind of covers some of those edge cases that they talked about too. As usual, feel free to hit me up. There's lots of good resources online that kind of animate the stack process where you can see it in action. If you want me to find a link for you like that, I think you can with a quick Google search, but if you're having trouble, let me know. I can find something more visual for you or do a video on more in depth on stacks. Otherwise, yeah, let's see your solutions. Bring on the questions. Otherwise, we'll proceed to the next challenge. Thanks.